Hi, my name is Lukas, and I'm here to present our paper Exploring Intentional Behavior Modifications for Password Typing on Mobile Touchscreen Devices. And my co-authors were Daniel Buschek, Matthias Kiermeier, Sarah Prange, and Florian Alt. So when you think about behavioral biometrics, there's a lot they can offer. So for example, they offer security, they are very fast, and most of all, they promise to be very convenient because the system simply monitors the user's behavior and no explicit actions from the user are necessary. However, if we think about it, this whole system very much relies on one single premise, and that is that users' behavior is unique to them and that it is very hard to intentionally change and also very hard to imitate. However, related work has shown that it is indeed possible to imitate behavioral biometrics. So in this example here, we had a mimicry attack with technical support by an AR application by Khan et al. And they were able to basically break this approach. Which made us think, okay, if they can do it with technical support, probably we can also do it like ourselves. So people could be able to just modify their behavior. And if you assume that, then there's a lot we could do. For example, we could use behavior as an explicit part of our passwords, or we could protect our own behavior by showing a different behavior in situations where it might be observed. Or we could solve one of the main issues with behavioral biometrics or biometrics in general, which is if the biometric trait is leaked, currently there's no way to recover. So if we assume it's unique and cannot be changed, then we cannot use this biometric anymore. However, if we can change it, then we could just alter our behavior. So this motivated our main question, which is, are people able to intentionally modify their behavior? And for this work, we looked at keystroke dynamics, that is typing behavior, and we looked at touchscreen devices, so smartphones. The roadmap to answer this question was to first of all figure out which touch features to use, then find a suitable visualization, because it's not trivial to show how behavior looks like to a user. And then finally, we designed a study to, as I mentioned, find out if participants are able, in general, able to modify their behavior, but also to explore what different influencing factors on this ability could be. So first on the selection, we here rely on previous work by Buschek et al., who found a total set of 24 different touch features that can be used for keystroke dynamics. And luckily, Khan et al. Did a correlation analysis on that and found the most important features, which are a total of 6 here. And we further reduced it to 4 features, which are, first of all, the touch area. That is the area with that I'm touching a specific key. Khan et al. Also had pressure, but we noticed that for our testing device, pressure was calculated from touch area, so we omitted that. Then we had flight time, which is the time between 2 key presses. Next up, we have hold time, which is the time that you hold down a single key. And finally, the touch-to-key offset, which is basically the difference between the exact touch point on a key and the key center. And here again, Khan et al. Distinguished this in X and Y position, and we just made one feature out of it. So the next thing was to communicate how a certain behavior should be performed. And for that, we explored a lot of different visualizations using markup and also pictorial designs. And finally, came up with 2 visualizations that we tested in an online survey with 114 participants. And their task was to associate the visualizations with given features. So they were shown a password with given behavioral modifications, and they should by themselves figure out which or what those modifications were. And the results for our winning design were over 80% of correct attribution of the features, and it was rated intuitive and readable and was preferred by the majority of our participants. And here's how it looks. So we used a design with key shapes as a metaphor, and a point indicating the touch point, and the size of the point indicates the area with that the key should be touched. Then the length of the key indicates the hold time of that key. The offset of the touch point that I just mentioned indicates where the key should be touched. And finally, gaps between keys symbolize the flight time. And the neat thing about this visualization is that we have both spatial features collected in the dot and both temporal features collected among one shared axis, which is the x-axis. So with this out of the way, we went forward to answer our initial question and did design a lab study with a total of 24 participants. And we designed 37 tasks using 3 different rotating passwords. And we wanted to explore quite a lot of things. So first of all, we wanted to explore all of the different feature modifications that I just mentioned before. Then we put those modifications at different positions within the passwords. We also wanted to combine all of the features with one another. And finally, we wanted to have a look at if it makes a difference if features are combined on a single key or distributed over the passwords. This resulted in this kind of complex study design where we first of all tested users' natural behavior. So we didn't give any clues on how they should alter their behavior. Second, we tested all of the 4 features in isolation with increasing numbers of modifications in a password. And lastly, we tried out all combinations. So this last part is a complete repeated measures design with the number of modifications and whether they were distributed or not. And also the session. So we in total had 2 sessions with 1 week apart. And in each of those sessions, participants had to execute all of the 37 tasks. And after each task, they would fill in a short experience sampling. And at the end of the session, we asked them to come up with behavioral modifications for a password on their own. And in the second session, we did this again. But in this case, we asked them to reproduce the modifications they had defined in the last session. And finally, we had a concluding interview. So on the right here, you can see our study application, which was an Android app using the Google open source keyboard project. And participants were shown the target behavior and had the option to practice shortly beforehand to get accustomed to that. And for the actual task, they had to reproduce the target behavior without the feedback that you can see here. So let's jump into the results. First of all, let's look at how the user's natural behavior looked like. And there are a few points to be seen here. First of all, we have a slight offset of touches toward the bottom right. This is not surprising, so this was also found in previous work and is most likely to the use of thumb input because the lower right is easier to reach. Secondly, you can see a secondary peak on the flight time, and we found this to be caused by the 0 travel time for double letters. For example, if you put in password, you have a double S, and there's no travel time between, so participants type that faster. Finally, you see this blob down here. We found that the touch area was correlated to the X position of the key. And here again, we think this is due to the use of thumb input, because if you're touching towards the left of your screen, if you're right-handed, then your touch will get flatter just naturally. So second, we looked at, okay, were people able to actually modify their behavior? And short answer is yes. What you see here is always the dotted lines indicate the target values for the participants. And on the right, you see a key shape again, with the dots here are, again, the target values that participants were supposed to reproduce. And what you can see is that we can clearly distinguish between different levels of those features, and also all of those were significant. However, what you can also see are, again, those secondary peaks on hold time and area. And they indicate that there were some user errors made, and I will come back to that later and explain why we think that happened. Next up, we also looked at the accuracy, so how large was the error that users made. And one interesting thing here is that the, again, offset was slightly to the right. So right offset was easier, less errors made there. And we also found a significant effect on the flight time caused by the session. So people were more accurate in the second session, and we think they just got accustomed to that. But in general, what we see is that people were better at performing default behavior. That was the behavior that's very close to natural behavior in comparison to more extreme ones. We also looked at the same thing corresponding to the number of modifications that a password had, and whether those modifications were distributed or collocated on a single key. And what we found here is that collocated features were generally easier to reproduce, so lesser errors were made. And also that with increasing numbers, more error was made, which is kind of to expect. However, we found that offset remained stable across both of those conditions. So neither the distribution nor the number of modifications had an impact on that. And we also find that the metadata that we collected supports those findings. So we found increased task completion time and reduced typing speed for more modifications and for distributed modifications. And we also saw more incorrect password entries for distributed modifications, and participants perceived the collocated modifications as easier from our Likert experience samplings. So far, we looked at individual users. So what we also did was look at the difference between users. And what we built here is a biometric identification model based on a Gaussian mixture model. Please note this is not optimized, and we did not intend to optimize it. It's just for the purpose of illustration. What you can see here is in blue the natural behavior, and then in orange the modified behavior. And what we found is that the biometric value is decreased when following modifications. That is, people are harder to distinguish. That's one point. And the second is, although they are harder to distinguish, there's still a lot of biometric value in this data. So they don't become the same. Finally, some user feedback. So we asked users what they found to be hard to control. And the main thing they mentioned was hitting the offsets, which was mostly to just hitting a key next to the key they wanted to. And another thing is that they sometimes had issues with distinguishing large area and long hold time because one was closely related to the other. and this is where the error from before comes in. So we believe this is the cause. And we also asked participants how they created their behavior modification for their passwords. And there are basically two common strategies to be found here. One is to just type the password down and then look at their behavior and put emphasis on anything they already did. And the other option was to use salient positions, for example, the beginning of words or syllables, or something that's in the word, for example, high score would have an offset to the top for the high. So quickly coming back to the initial motivation, we had a quick look if extending password space would be a realistic option. And we built a random forest classifier to detect the modifications, so to distinguish them, which was possible with high accuracy. And we also calculated upper bounds entropy for that. And just to illustrate, for example, if you compare a password with no modifications, then we get the same entropy if we use 3 modifications, but we can use 2 less characters. However, please note there is more work to be done here. So we don't know what different keyboard layouts can do or different hand postures. And also, as we have seen in the user feedback, there might be common patterns that might reduce the password space. So to conclude my talk, here are a few takeaways. So first of all, to answer our initial questions, yes, participants were able to intentionally modify their typing behavior. And we also found that it is theoretically possible to use this to extend password space. We found that modifying less and collocated features was easier for the users. And the final thing that I want to stress is that I would like to leave you with a new perspective on typing behavior, and that is understanding it not only as an implicit byproduct of interaction, but rather as something that we can actively control and that we might further explore in future work. And with that, if you want to have more detail and discussion, I would refer you to the paper or just ask right away. Thank you very much.
So we have time for about 3 or 4 questions. Oh, you're all being very sleepy before lunch. Okay. So I think my first question would be about the offsets.
Yes.
It seems like that is particularly more difficult than some of the other modifications. And I was wondering if your participants reported that back as well, that just on phone screens, the keys are so small, and sort of doing that offset felt more difficult. And then I'd also wonder if there's an age distinction that comes up there where older users, and I don't know if you had any age breakdown in this or if you had enough participants to do it, were more concerned about sort of like, this is just impossible at that point.
Okay. Yeah, first of all, we did unfortunately not look at age, so I cannot answer that. The second one is yes, definitely users reported that it was hard, and they also suggested, for example, that you might use it for input like PIN, where you have bigger keys or on a tablet. But we also think that for practical applications, you might have some tolerance, for example. So it wouldn't be an issue to hit a neighboring key as long as we know it's close to the point that the user should have hit. And I think there can be a lot done to improve usability there if you would build a system.
This comment is completely orthogonal to the purpose of your talk, but I was interested in the entanglement between the area covered and hold time, just because there's metaphorical entanglements of bigness and length of time, space-time entanglements, and so this is a physical sort of instantiation of that entanglement, which is interesting. I have a cognitive linguistics background, so it's interesting from that point of view, even though it was completely not what you were going for.
Anne-Marie Hoiker from Central Michigan University. When you were looking at flight time and, you know, that you said it was less flight time, did they have, and two-part, I'm looking at the too close paradigm. Sometimes it's harder to hit keys on a small keyboard that are too close to the one you're on now. Mm-hmm. And you mentioned that the double letters had less flight time, but were they, you know, when they hit the second letter, were they always accurate on the second letter, or did the repeat cause a stutter where they got multiple letters, or if they tried to hit the letter right next to where they were supposed to be, you know, the fineness of control to get only, you know, 1/8 of an inch over as opposed to moving 5 keys over?
So what we saw in the data is that this peak that I pointed out is really from the same letter, mm-hmm. So there was no flight time involved there. We did not look at like very close proximity versus larger proximities.
Hey, Dan Cosley from Cornell and NSF again. So, you know, I think it's kind of interesting to think about this. It reminds me of a little bit of stuff like the emotion mouse and stuff from over in HCI land, where people have tried to use keyboard and mouse pressure as input into systems, right? To do interesting things. So the big question for me about this as a technique for password entry is you mentioned what people sort of passwords they created. Did they say anything at all about whether they thought it would be interesting or fun or useful or better or worse than the way they think about passwords right now?
Yeah, so we asked them about that, and participants were kind of divided on that. So a lot of them really liked the idea and thought it would be cool to have, and a lot of them had, they were worried about things that we also see in behavioral biometrics in general, which would be things like, will I be able to reproduce my own behavior under certain circumstances, for example, if I'm in a hurry, etc. So those were the main concerns when using it, but in general, they were very positive.
Okay, great. Thank you so much.
Thank you.